Hi folks, this is Mr. Pinola, and today we're going to take a look at Newton's three laws of motion, something maybe you've talked about before, but we're going to see if we can learn them a little bit more in depth today. Sir Isaac Newton, the man you see on your screen, developed three laws of motion in 1687 in his book Principia, which you see pictured on the right. Let's take a look at some of those laws. Newton's first law of motion, which some people call the law of inertia, and we'll discuss why that is later on in this video, has essentially two parts to it. The first part of the first law states that an object at rest will remain at rest unless it's acted on by an unbalanced force. The second part states that an object in motion will remain in motion with the same velocity unless it's acted on by an unbalanced force. So a couple things that we need to think about before delving into this description of the first law. First off, what is an unbalanced force? An unbalanced force basically is anytime you have a situation in which the total amount of force going one way is bigger than the total amount of force going another way. If the forces going two different directions are equal, then they are balanced. But if one force is larger than another, then they are unbalanced. Let me show you what I mean by that. Here's a closer look at Newton's first law, part 1. Notice that we have a tug-of-war basically going on here between the blue team on the left and the red team on the right. And we have a wagon in the middle. The wagon is the object that is at rest. And that wagon is going to remain or stay at rest unless it's acted on by an unbalanced force. But take a look at the diagram. Are those forces unbalanced? They're not. Those are balanced forces because you have 100 newtons going left and 100 newtons going right. So since the forces are balanced, that means the wagon will stay at rest, according to Newton's first law of motion. But how about this example? Now an extra person has been added to the team on the left. So the left team is pulling with 150 newtons, and the right team is pulling with 100 newtons. Well, now the forces are unbalanced. There is more force being pulled by the team on the left. And so that means that now the wagon will accelerate, meaning that it's going to start changing its speed as it gets faster and faster moving to the left. You might notice also something else. Since there's 150 newtons going left and 100 newtons going right, if we consider the difference between these two forces, that's 50 newtons. There's 50 newtons extra going to the left. That means that 50 newtons is the net force, or the combination of all the forces acting on the wagon. Something to keep in mind. Let's now take a look at the second part of Newton's first law, which states that an object in motion will remain in motion with the same velocity unless it's acted on by an unbalanced force. Remember, velocity includes something's speed and the direction it's traveling in. So this law basically says that if the forces are balanced, an object is going to keep going with the same speed and in the same direction until there are unbalanced forces acting on it. Take a look at this picture. This is an out-of-control car. The car is going to keep traveling forward with the same speed until there is an unbalanced force that acts on it. Maybe until it comes to rest because somebody has hit the brakes. Maybe it hits into a wall or something like that. Unfortunately, we hope that doesn't happen, but that would be an unbalanced force. Or maybe the person hits the gas. That would be an unbalanced force that would cause it to get faster. But basically, unless the driver hits the brakes, it slams into something, or the driver hits the gas, or if they turn the steering wheel and cause it to change direction, unless one of those things happen, that car is going to keep going forward at the same speed. And that's what Newton's first law, part 2, states. Here's a little animation to show you that. There's a little pig, and the pig is sliding along this icy sidewalk. And notice the pig is trying to stop. However, the pig can't stop. The only way it's able to stop is if it grabs onto that tree branch that's hanging over the side of the lawn. Well, by the pig grabbing onto the tree branch, the pig is using an unbalanced force to stop its motion. Otherwise, the pig would have just kept moving forever and ever and ever down the really icy sidewalk, or at least until friction took over. Now, one last thing to keep in mind. You might remember that I talked about something called inertia at the beginning. We say the pig couldn't stop in this example because it had inertia. The more massive something is, the harder it is to stop. So if this pig was larger, then it would have needed more force to actually come to rest. Inertia is just your tendency or your likelihood to keep doing what you're already doing. So big objects are harder to get moving if they're currently stopped, and they're also harder to stop moving if they're currently in motion. That's what inertia is, and that's why the first law of motion is sometimes called the law of inertia. So in summary, that's the first law. An object at rest is going to remain at rest unless it's acted on by an unbalanced force. And the second part states that an object in motion will remain in motion with the same velocity unless it's acted on by an unbalanced force. If you're taking some notes, now might be a good time to pause the video and take down some of this information. And keep in mind, you can always go to your teacher's office hours to ask them to clarify or give you more examples of the law. But let's move on now to the second law. Newton's second law of motion, in my mind, also has two parts. The first part states the net force acting on an object directly affects the object's acceleration. The second part states that the mass of an object inversely affects the object's acceleration. Now, there's a lot to unpack here. We've got to understand some vocabulary before we keep going. First off, you might see the word net force. Well, keep in mind from the last example, the net force basically is an indication of how much stronger one force is than another. So this is, if there is a net force, it means the forces are unbalanced, and it's saying how unbalanced are those forces. It's like the combination of the forces acting on the object. Also, notice the word acceleration here. We learned acceleration a couple weeks ago. Acceleration means that something is changing the speed it's currently at. So if something has a big acceleration, it means it's getting faster and faster and faster, or slower and slower and slower at a very quick rate. So it's changing its speed quickly. Also, notice the word directly. Directly means that if one thing increases, the other thing increases with it. So that means, according to the first part of the second law, if the net force goes up, that means the acceleration will go up as well. We'll explain that a little more in a moment. Notice the second part, though, mentions inversely. That means if one part goes up, that the other part goes down. And so we'll talk more about that as well. So let's delve into the first part of the second law, which states that the net force acting on an object directly affects the object's acceleration. Here's our tug of war example again. Notice in both cases, the blue team is going to win. In both cases, the blue team is going to get the wagon to accelerate because they are pulling with more force than the red team. That's what the first law said. But the second law talks about how quickly the wagon is going to pick up speed. In the first case, the net force is 50 newtons because there's 50 more newtons going to the left than to the right. But what's the net force in the bottom picture? If you said 150 newtons, you'd be correct. That's because there's 150 more newtons going to the left than there are to the right. And that means the net force is bigger in the bottom picture. Since we said that the net force directly affects the object acceleration, that means that in the bottom picture, the object will have a bigger acceleration, or it's going to pick up speed more quickly because there's a bigger net force. This is kind of like if you have two identical cars, but you put a stronger engine that can use more force in one of the cars. That car is going to be able to pick up speed more quickly than the other car. But now let's take a look at the second part. This is where we talk about mass. The second part of the second law states that the mass of an object inversely affects the object's acceleration. Notice in this case, I kept the net force the same. It's 50 newtons in both pictures. However, in the top picture, the mass of the cart is 5 kilograms. But in the bottom picture, the cart is more massive. Now it's 10 kilograms, meaning it would ultimately weigh more if you were to put it on the same scale on Earth. In both cases, the cart is going to accelerate to the left. However, in the bottom picture, the cart is going to speed up a little bit faster. I'm sorry, I misspoke. In the top picture, the cart is going to speed up a little bit faster. That's because in the top picture, the cart has less mass, so it's easier to change its speed. In the bottom picture, it has more mass, so it's harder to change its speed. So even though the net force is the same in both cases, in the top picture, the cart is going to change its speed much more quickly, and that's because it's only 5 kilograms as opposed to 10 kilograms in the bottom. So let's recap the second law of motion, and now is some time where you might want to take this down and take some notes on the second law. The second law has two parts, just like the first law. And the first part states that the net force acting on an object directly affects the object's acceleration. That means if there's more force, there's going to be more acceleration, and the object will speed up or slow down more quickly. The second part states that the mass of an object inversely affects the object's acceleration, meaning that essentially the heavier an object is, the slower it's going to change its speed. That would be like if you were to put the same engine in two cars, but one car was much heavier than the other. Even if you push the gas pedal all the way down on both cars, the lighter car will speed up more quickly than the heavier car. Let's move on now to Newton's third law of motion. And Newton's third law of motion just has one part to it. It says that for every action, there is an equal and opposite reaction. Maybe you've heard that phrasing before. Let's take a look at it. Well, every force comes in pairs. That means every time you use a force, there is a force back against you. For example, if I hit the table in front of me, the table hits back against my hand. The action force is that the hand hits the table. The reaction is the table hits the hand. That's why I can feel the table when I hit it. So take a look at this picture. Here you have a swimmer who's pushing off against the wall. Well, the swimmer is going to push against the wall. Take a look at the arrow going to the right with a force of 100 newtons. They're pushing into the wall. Maybe you've experienced that before. But what actually causes the swimmer to move is that the wall pushes back on the swimmer with exactly the same amount of force. That's why if the swimmer pushes harder against the wall will push harder against the swimmer to send the swimmer flying at a faster speed. And so this happens every time you have two forces. Let's see another example of that. Here's a man hitting a baseball. Can you identify the action and the reaction forces here? Well, the action force is that the bat hits the ball. What's the reaction to that? We'll just flip the words around. The reaction is that the ball hits the bat. That might seem weird. How does the ball hit the bat? Well, if you've ever played baseball or softball, maybe you've noticed that when you hit the ball, sometimes you feel a little sting in your hands because the ball has hit the bat and it's caused it to shake a little bit. That is the reaction force of the ball hitting the bat. Here's a close-up picture on the right of the moment of impact when the ball hits the bat. Remember, action is bat hits ball, reaction is ball hits bat. Now you might be puzzled by this. If the bat hits the ball with 100 newtons of force, that means the ball hit the bat with 100 newtons of force. So why then does the ball go flying, but the bat stays relatively where it is? Well, we have to think about the mass. Notice that the ball has such a tiny mass, at least compared to the bat and the person swinging the bat. That means the ball, when it experiences a force of 100 newtons, is going to go flying. But the bat, when it gets a force of 100 newtons, won't be as affected by it. They still experience the same force in opposite directions. The ball got hit forward, the bat got hit backwards, but the ball was more affected by it because the ball had less mass. So anytime you have two objects that collide, the forces on them are always exactly the same. But sometimes it might seem like one object is more affected by the force. That's just because it has a different mass, not because the forces are different. So if you wanted to take some notes on Newton's third law, now you know a little bit more about it. And it states that for every action, there is an equal and opposite reaction. And I just want to clarify that when we say equal, we mean equal in amount. And when we say opposite, we mean opposite in direction. So just like that swimmer picture, the force of the swimmer on the wall and the wall on the swimmer were equal because they were both 100 newtons, but they were opposite because the swimmer pushed to the right on the wall and the wall pushed to the left on the swimmer. So that's it. We've taken a look at Newton's 3 laws of motion, and let's sum those up quickly for you. These are not very scientific words I'm using, but maybe this will get the point across to you a little bit better. In summary, anytime you think about Newton's first law, you need to think about inertia. And inertia is basically this property that matter has that says that everything is going to continue doing what it's already doing, unless there's an unbalanced force that acts on it. So if something is sitting on a table, like my phone is sitting on the table right now, it's going to keep sitting on that table until I apply an unbalanced force. But like a car that's moving down the street, the car is going to keep moving down the street unless there's an unbalanced force that causes it to turn, stop, or speed up. The second law pretty much says that if you use a lot of force on an object that has a very small mass, it's going to change its speed really quickly. That's why if you put a really powerful engine in a very tiny car, that car is probably going to change its speed really fast. But if you put a weak engine in a big bus, the bus is going to take a long time to speed up or slow down. And lastly, the third law says that action and reaction forces are always equal. So for example, if a bat hits a ball, the bat hits the ball with 100 newtons, and the ball hits the bat with 100 newtons in the opposite direction. Sometimes it might look like one object is more affected by the force, but the forces are still the same. It's just that because of the different masses, they might experience different accelerations. I hope you enjoyed that video, and I hope you learned a little bit about Newton's 3 laws of motion. You can look in your textbook, or if you can talk with your teacher at office hours for a little bit more about those. There's obviously some stuff that we left out along the way, but this should hopefully give you a pretty good idea of how Newton's 3 laws work. Hope you're doing well at home, and make sure to do the work that follows this activity. Take care.